Hi, this is Dr. Bay, and today we're going to go over the fundamentals of radical reactions. So stay tuned.
Organic chemistry,
Taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy. Soaring through the sky, triumphantly we fly, give rise to the complexity of life. Living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
So just as a reminder, chemical bonds can be broken in two different ways. Heterolytic bond cleavage uses double-headed arrows to show the motion of two electrons in order to produce ions, while homolytic bond cleavage uses single-headed arrows, also called fishhooks, which show the motion of one electron in order to produce two radicals. The strength of a carbon-hydrogen bond is inversely proportional to carbon radical stability. So this means that the more stable the resulting radical is, the weaker the bond. To visualize this in a more quantitative way, we can look at the bond dissociation energies, or BDE values, of the following carbon-hydrogen bonds for these four molecules. The lower the BDE value, the weaker the bond, therefore making its radical more stable. Now let's look at these molecules after each hydrogen atom in blue has been homolytically cleaved to form each of their corresponding radicals. Recall that radicals are actually considered to be neutral since they have no formal charge, but they're technically still electron deficient since they have an incomplete octet. The order of stability for radicals follows the same trend as carbocations. Methyl radicals are least stable, while tertiary carbon radicals are most stable. Resonance-stabilized radicals are more stable than tertiary radicals, which includes both allylic and benzylic radicals. Vinylic radicals, however, are the most unstable types of radicals because these are when the radical is directly on an alkene carbon atom. This is because a radical in an sp2 orbital is less stable than one in an sp3 orbital. Now, when thinking about how to draw mechanisms of radical reactions that involve single-headed arrows or fishhooks, there are 6 patterns that you may come across. First, homolytic cleavage is when a single bond breaks to form two separate radical species. Second, two radicals can couple together to reform a single bond. Third, hydrogen abstraction can occur where a radical can abstract a hydrogen atom from a compound which would generate a new radical. Now, this is different from a proton transfer that you've seen before because in a hydrogen abstraction, both the hydrogen atom and its electron are being transferred from one location to another, whereas in a proton transfer, only the hydrogen atom is being transferred. And fourth, halogen abstraction can occur where a radical can abstract a halogen atom to generate a new radical. This step is similar to hydrogen abstraction, except a halogen atom is being abstracted rather than a hydrogen atom. Fifth, addition to a pi bond is when a radical adds across a pi bond and generates a new radical species. And the last pattern is elimination. If the carbon radical was labeled as the alpha position, a double bond forms between the alpha and beta positions. This would result in a single bond at the beta position being cleaved, causing the molecule to break into one alkene and one radical species. Now let's look at the radical mechanism for chlorination of methane. Radical mechanisms generally consist of 3 parts. The first part is an initiation step, which is when a radical species is formed from a non-radical species through homolytic cleavage. In chlorination of methane, 2 chlorine radicals are made where 2 single-headed arrows are drawn to show the breaking of a single bond and the formation of 2 radicals. The second part of the mechanism is propagation, which is when a radical reacts with a non-radical species to form a new radical and a non-radical species. For chlorination of methane, propagation is a two-step process. The first step is hydrogen abstraction, where an HCl bond is formed from a Cl radical. Two single-headed arrows are first drawn to show the breaking of the CH bond to form two radicals, and the third single-headed arrow from the Cl radical couples to form an HCl bond. The second step of propagation is halogen abstraction in order to form the desired product and to regenerate a Cl radical. In this step, two single-headed arrows are drawn to show the breaking of the Cl-Cl bond to form two radicals, and the third single-headed arrow from the carbon radical couples to form a carbon-Cl bond. And the third part of the mechanism is termination, which occurs when two radical species react to form a non-radical species. In chlorination of methane, several radicals collide and couple to form several possible products. When you draw out a radical mechanism, however, it's not necessary to draw all of the possible termination steps. Just focus on the one that produces the desired product in the problem. So in summary, radical mechanisms use single-headed arrows that show the flow of only one electron. Resonance-stabilized radicals, like allylic and benzylic radicals, are more stable than tertiary radicals. Furthermore, a radical mechanism typically consists of three parts: initiation, propagation, and termination. And there are several patterns in radical mechanisms, including homolytic cleavage, coupling, hydrogen abstraction, halogen abstraction, addition to a pi bond, and lastly, elimination.
Organic